So here's the way structure forms in the universe. Stuff is amorphous and triaxial. Okay, let's reuse that word, just like with the ellipticals. And along one of those three primary directions, it's going to be flattest, and that's going to have the largest density contrast, and that's going to make the galaxies in that particular direction collapse in that direction quickest. So if you think of just a randomly shaped lump of clay, the direction along which it's already flattest is going to be the direction that it gets flatter still the quickest. So three-dimensional random lumps tend to turn into two-dimensional pancakes. And then the two-dimensional pancakes tend to collapse along the next dimension that has got the highest density contrast into filaments. And then the filaments will have some denser middle somewhere, and that'll be where the filament drains into actual zero-dimensional lumps, galaxy clusters like this guy right here. Now, the speed with which you do that is going to be quicker if you have more density contrast, if you're a bigger, more massive cluster. And it's going to be much more lazy and dawdling along slowly if you are a poorer cluster. And so you just take a single moment in the history of cosmology, like today, and take a photograph and look at it all. You expect then to see different of these lumps, these overdensities, at various stages of this evolution. So you see sheets, like pancakes, and you see filaments, and you see lumps, clusters of galaxies. You see it all in different stages, and they're all kind of tending towards becoming cluster lumps, okay? So heading towards a meatball topology, but nowhere remotely close to being there yet. Okay, so now we're beginning to look at the universe with infrared, and now we're going to look at the plane of the Milky Way galaxy, and it's now along the edge here. These three-dimensional views of a spherical sky, then compressed onto a flat surface like a slide, are always going to look, it depends on how you flattened out as to how it looks. So this is also the plane of the Milky Way. So this is half of the plane of the Milky Way, and then the surrounding is the other half of the plane. So it's kind of a mind trip to try and figure out how to turn that into a thing. But so imagine grabbing here, and then smoothly yanking them around out of the plane of your computer screen into right beneath your nose, so that this spot and that spot are the same place. And then button up all this too. So it's kind of like a dumpling or a, what do they call those things? They're really tasty. Anyway, those Asian, somebody help me here. I used to buy them all the time at Trader Joe's. Yeah, gyoza. Like that, right. Or, no, it's not the word I'm thinking of. Anyway, if you could really do it perfectly, it'd be a nice spherical thing. It wouldn't have any seams. But that's what you're looking at. Anyway, we're getting off topic because it's dinner time. Here's what I want you to pay attention to. Look at all the filaments. Now you can still see filaments here. And that's because they did something extra. They actually color-coded the galaxies according to how fast they're moving away from us, which is a decent proxy for their distance. And so you see this filamentary universe. It's really obvious. And even more obvious in this picture where I think they probably projected it a little bit better. Clearly we live in a filamentary universe. This, of course, is our own galaxy. And trying to see the rest of the universe while you're also in the middle of a galaxy can be difficult in some directions. I'm going to let you click on that and watch as you can cruise through space. We don't have an extra 17 minutes to spare, but you can do that on your own. So Joel Premack, superstar cosmologist up at UC Santa Cruz, and whom I had the privilege of working with for many years in the 1990s, he got the best code in the business. He's got the biggest supercomputer. He's got the biggest team. He's got the best people. And he's got the best cosmological simulations, starting from different assumptions of what the universe must have started like, and then evolving it forwards, millions and millions and millions of particles at a time, of both dark matter and even fuzzy, squishy particles called gas that can do things that dark matter can't do, like squish together and get rid of some energy and collapse and become stars and then shine with a certain amount of light. And you can actually see the evolution of the universe. And he's got some nice YouTube videos that show that. Unfortunately, I can't show you the video because we don't have time, but I can show you a slice out of it. This is mostly dark matter, but you see the yellow lumps in there? Those are where galaxy clusters would form. So again, you see lumps, and then you see pancakes, and then in the pancakes you see filaments, and then in the filaments you see lumps. Three-dimensional, two-dimensional, one-dimensional, and zero-dimensional density contrasts, density inhomogeneities. And I want you to notice how similar this is to the galaxy patterns that we saw. And this was a simulation using pure cold dark matter. And so we feel pretty confident, and there's a few people who want to keep us honest and say, well, maybe there's some warm dark matter out there. We're not totally ruling that out yet, but really, you know, most of the people would say we can explain exactly what we see very, very, very well with just pure cold dark matter. And since it's simple, let's go with it until it shows that it can't work. So far, it's working fantastically. So here's a box, a simulation box. And you can go on YouTube and you can see the evolution of something like this. You begin with a box that looks totally uniform to your eye, but yet there are tiny lumps in there. And those lumps amplify because gravity makes lumpy places look even lumpier and lumpier. And the more density contrast you get, the faster they lump together. And you can see this kind of this filamentary, spaghetti, capillary, I mean, there's a lot of different names you could use to describe it, kind of a structure forming. And that's exactly what we see when we look at the real universe. There's lots of pretty videos and pictures that show this. And while Joel's group may be on top of the heap, there are actually a lot of other groups around the world that are also doing their own simulations. Little changes here and there to different codes, and that's always a good thing, because if you see little differences, you can try and figure out, why does yours look a little different than ours? Well, let's look at our assumptions, and you know, and that's how you learn. All right, so gravity is all we need to make large-scale structure, and that was what we hoped, because that's nice and simple. I guess maybe you would have hoped, maybe not, if you were looking for mystery, more mysteries. But anyway, we still got plenty of mysteries. We don't know what the dark matter is, and there's even more mysteries to come as you watch the video later on the runaway universe. Okay, but pure cold dark matter is what works. We just want to hammer that in. So the next question is, how old is the universe? So by measuring the expansion rate today, we can run the movie backwards and see when everything was in one place. So when we measure the expansion rate today, we now have pretty good measures of Cepheid variable stars. Cepheid variable stars in nearby galaxies. With a Hubble Space Telescope, we can see Cepheids out all the way to the Virgo cluster. And that's far enough to really start to get a good number here, 70 kilometers per second per megaparsec. Looks like what H is locally. So Cepheids is our distance indicator, but then you can go farther by using an even brighter and therefore more distantly visible distance indicator that we talked about a little bit before, and that's type 1a supernovae. They're all the same. They're all 1.4 solar mass white dwarfs getting dumped on by their companion until they finally get squeezed so tight by the extra burden of all that matter that the carbon that they're made of will actually get pushed hard enough to begin to ignite, and then all the carbon goes up at once because the carbon is only supported by electron degeneracy pressure and not by gas pressure, and so there's no way really to halt the explosion once it begins, and the whole thing blows up. There's nothing left over, no gravitational lump left over that you have to try and account for and would complicate trying to turn it into a standard candle. They all blow up perfectly, and they're all the same mass, and they're all pretty much the same thing. And you can see these things as far as the edge of the observable universe because they are the brightest things out there. They're even brighter than galaxies themselves, at least early galaxies, which were smaller than the ones we see today. And they allow good determination too. And I think I need to update this a little bit because there's actually some tension beginning to show up between the type 1a supernovae that are far away and the type 1a supernovae and the Cepheids that are nearby. And the differences in H that we get is like 67 to 68, all the way up to 71, maybe 72 kilometers per second per megaparsec. A little bit more than statistical randomness could account for, and people are beginning to wonder, gee, is that real? And what is that telling us? Oh, these are just pretty pictures. That's a type 1a supernova. And that's the same type 1a supernova. And so is that, and so is that. This is a gravitational lens caused by a nearby galaxy imaging a galaxy in the background that happens to have a type 1a supernova going off. Pretty cool. Oh, wait a minute. No, sorry, take that back. I should have read my own. That's not a type 1a supernova. It's just a quasar. I was starting to think, gee, you know, those don't last very long. Is there really that many? No, these are distant quasars, okay? Now, the neat thing about gravitationally lensed quasars, point sources of light, is that you can follow. Remember, the neat thing about quasars is they change their brightness. Their brightness can change significantly in as little as 1 day. And a week or a month or, you know, a few months is very typical. And so what they do is they monitor the brightness of each of these images, knowing each image is exactly the same thing. And after a while, after you've discovered one of these things, you can see that, oh yeah, this one's doing exactly the same thing as this is, but this one's offset by, you know, 6 weeks. That means there's 6 weeks of extra light travel distance following this path than following that path. Well, that's an actual physical distance, and we know the optics of gravitational lenses, and it allows us to tell the distance very accurately of this galaxy and this background quasar. And that's another way to get a good distance indicator, entirely separate. So you measure the time delay in the variation between these different images of the very same thing, and that gives you 72 in excellent agreement. Okay, now we ask a different question. How dense is the universe? When really was the beginning? So we want to ask, how old is the universe? How old is the universe depends sensitively on how much density there is. How dense is the universe? If the universe is really dense with matter, then this is the evolution you would expect. There's the Big Bang, it expands. Okay, now I want you to, let me just pause. This is not the size of the universe. That's actually a meaningless idea. you can't put a boundary around. You can't get outside the universe and watch it happening like a lump over there. I know it's very tempting. I know that's what you want to do, but you have to stop yourself from doing it. You, the observer, have to remain inside the universe. So instead, we're not plotting the size of the universe. We're just plotting the distance between galaxies. Pick a couple of galaxies, plot the distance as it evolves, as the universe expands. Okay? So it expands rapidly and then it slows. It slows. Why? Well, because there's gravity trying to pull it down. Now, what we know today is that the rate of expansion of the universe is matched by the slope right here. That's an observational constraint. That's basically expressed by the Hubble constant, the Hubble parameter, h, 71 kilometers per second per megaparsec. So if the universe is very dense, more than the closure density, maybe a lot more than the closure density, then it began actually not that far into the past. The universe would be younger in that case to get to this point. And then look at what happens. It gets to some maximum size and then it collapses again to the big crunch. This is the big crunch. You can have a big bang, why not a big crunch? That sounds like the ultimate trash compactor. There you go. Now, if the universe is exactly at closure density, then it evolves like this. It starts further back right here. And it expands and it slows and it slows and it slows and it slows and it slows, but it never really comes to a stop. The rate at which it slows is quicker here because there's more gravity because it's all dense. But notice that the rate at which this curvature gradually curves gets less and less. And it gets less and less because the universe is getting more and more spread out and gravity is less and less able to pull it back. So you can convince yourself, if you think about that, that there is a density such that the universe would expand but never ever quite come to a stop, let alone recollapse. But after infinite time, the density of the matter would dilute all the way to zero. And what have you got at that point? You've got a universe with exactly zero density. We usually express density with a Greek letter rho. And it's also got an expansion energy that is also zero. If it has zero density, it's also got zero gravitational energy. This is a universe with exactly zero total energy. This is the kind of universe that we know from the existing laws of physics that are so well verified how to create. You can create a universe like this out of nothing. A universe from nothing. Now, you could go the other way and say, well, what if you have a universe that's got too much expansion? Then it maybe curves a little teeny bit down here, but then it just keeps going and going, and it's pretty much kind of a straight line almost. And even after infinite time, it's still going. It's still got some positive velocity. So that would be a universe that has less than the critical density. Now, if we were in a universe dominated by only the ordinary matter, we know how much density there is. There's only 4%. 4% of the matter is ordinary matter, 4% of the closure density. So if the ordinary matter is all there was, then we live in an open universe. But we've never been happy with that conclusion because we don't know how to create a universe like that. It's just, we can't, there's no way we can figure how to do that. We know how to make this universe. We'll talk more about that later. But not that one, and not this one either. I mean, you really got to scratch and claw and, throw a whole bunch of weirdo physics around to try and make a universe that's like this or like this. The natural, easy, simple, Occam's razor-y way to make a universe gives you one that's like this. So this is the one that we've always been happy with. I'm going to draw a smiley face. This is what we want. This is what we like. This is what we hope is true. Okay, call it a bias if you want. We're happy to change our minds if the universe tells us we have to, but actually we'll see, no, this is actually what looks like what we got. Okay, so if we really believe this is what we got, and yet that's all the ordinary matter that there was a time when we thought that, okay, I guess all the rest of it's dark matter. 96% of the universe is dark matter? Gee, that's a lot. Well, okay. For a while, observations weren't good enough to show whether or not that was really false. But as we got into the 90s, the evidence got better, and it really did look like maybe it was false. And there was even a time when we thought, well, how do we solve that? And Joel Premack had a great idea. He said, well, you know, there is one dark matter particle that we know for sure exists. It's called the neutrino. What if we had neutrinos, and then whatever this cold dark matter particle is, and most of it's cold dark matter, but if we just cook the recipe a little bit, if we just throw in a little extra paprika in the form of neutrinos, then we could get the clustering of the universe to slow down at a rate that agrees with what we actually see. And so I was part of that team, and I was the one who was doing the identification of galaxy clusters, both in the numerical simulations and in the real universe, and comparing the two. And it really looked like, gee, you know, if we just had a mass for that neutrino, we know neutrinos are out there. We know roughly how many of them are out there even. And if we just had a mass of 5 electron volts, that's not asking very much. If we just had 5 electron volts, then 20% of the dark matter would be hot dark matter. And we talked about this before, how hot dark matter is zipping around so fast it just free streams away from any lumps, and basically it inhibits the ability for galaxy clusters to form, and it would inhibit them in a way that would agree very nicely with observations. And actually from 1992, I think I joined the team, up to 1997, I mean, it was looking better and better. And there was a time, I still remember, when Joel phoned me at Cabrillo College and he said, the first results from the LSND, the liquid scintillator neutrino detector experiment at Los Alamos Labs, trying to measure the mass of the neutrino, the electron neutrino, their first results are in. Guess what they found for the mass of the neutrino? And I paused and I said, you're not going to tell me 5 electron volts. And he said, 5 electron volts. And so that was exciting. I mean, had Joel, with our help, me and Doug Hellinger and Anatoly Klippin and a few other people, mostly that little nugget of people I just mentioned. Could this theory actually be right if we actually figured out the large-scale mass of the dark matter? Is it really 80% cold and 20% hot? Well, that was very euphoric. That was wonderful, but it didn't last. Somebody pointed out that, this corner of the detector looks like it's, might be contaminated by this other source that could be giving signal that mimics these neutrino masses that we're inferring. And really, I think to be totally sure, we have to exclude that part of the detector. And the other researchers in the team said, well, you make a good point, I suppose, but you know what? That's where all of our signal is. If we have to throw away that corner of the detector, then we don't really have a statistically significant answer yet. Which is sad, but, if that's the way it is, that's the way it is. So, of course, we're all hoping that they would redo the experiment. But instead what came along is the government said, this is all great equipment. We need it. We need this to test nuclear bombs. And so the experiment never got repeated. And then I ended up with osteonecrosis of the femoral head from poison oak. And anyway, a long, sad story. And I was not doing any research for a while because I was devoting all my time to understanding bone and cartilage and medical stuff because my doctors were really being entirely lame. And I did save my bone from going through osteonecrosis with some very unconventional stuff, but medically accurate and, not homeopathy or anything ridiculous like that, but I mean, some good stuff. But I had to work really hard, and then a year after that came the discovery that gets us back on track here. Okay, so enough of my sad story. My research life had a wonderful peak there when Joel called me, and then after that it's been a long bear market. But we don't have to get depressed about that because we do know a lot more now. We did learn some really cool stuff towards the end of the 1990s. That was a standard Big Bang model, dark matter, and a little sprinkling 4% of ordinary matter. But this standard Big Bang model already had problems with it. And so we need to talk about that. Okay, we still got half an hour till I have to end this lecture. Okay, problem number 1 is the age of the universe as measured by the Hubble law disagrees with the age of the oldest globular clusters. So if H is 70 and we're at critical density, that implies the universe is only about a little more than 9 billion years old. Again, let's go back. Oops, too far. Here. So if the universe undergoes this kind of curvature, it means that the beginning of the universe is earlier than, what would be a straight line constant velocity. And so here, more density means more density in dark matter, all the way up to closure density, means that the universe actually begins earlier. Not as early as this red one here, but you get the point, okay? More curvature means the universe started younger. Well, that's a problem because we've already age dated the globular clusters, and we know stellar evolution very well, we think. And it's pretty hard. The globular cluster age people, they're very diligent, hardworking people. And they said, you know what, we can't give you 9 billion years. No, these are 12.5, 13, 13.1, 13.2 even billion years old. I'm sorry, you're going to have to just deal with it. You cosmologists are going to just have to deal with it. Okay? So, how are we going to deal with it? Well, the type 1a supernovae look like they might help solve it because these are visible from so far away. We could really check the expansion rate of the universe going back not just to the local galaxies with their Cepheids, but all the way back to most of the way to the beginning of the universe, or at least halfway. And that's enough. So, I mean, obviously the pictures look pretty ratty when you're looking at type 1a supernovae that are this far away, but that's okay. All you really need, you need to get a spectrum, and you need to see their maximum brightness. If you can get that, you're in business. So this slide, I mean, I like that all these points lie on top of each other, but it's kind of a complicated diagram to explain, so I'll just say that this is really telling us that the type 1a supernovae really are all alike once you've corrected for their different metallicities. So, I kind of left the project there with Joel's group in 1996 and a half, 1997. Early 1997, I developed osteonecrosis. I quit all research except in my own medical situation. I'm spending all my time going up to UC San Francisco and camping myself in the cellar down there where all their journals were and learning everything I could about the biology of cartilage and everything else. Meanwhile, what was happening was the video you guys are going to see at 7:30, and that is they discovered that the universe is not slowing down like we thought. It's accelerating. Now, Brian Schmidt, you'll see on the video, when he first saw that the data indicated this, rather than be elated that he had discovered an incredible new property of the universe, he was, as he said, horrified. So I think what's admirable is that, horrified or not, he stuck with it and is like, okay, you know what? We really want to know what the truth is. This is what I love about hanging around scientists. You don't see that attitude around politicians or priests and religious people. It's so wonderful, anyway, to be around. People actually want to get it right. We really want to know what's the actual truth here. Now, luckily, there was another group that was doing the same kind of work, led by Saul Perlmutter. And so it's kind of, I can imagine what the conversation was really like, as they kind of, were starting to talk to each other, and nobody really wanted to admit that, you know what, I got these crazy results that can't possibly be right. But they sort of both kind of inched towards it, and they both realized that, you know what? Oh, thank God, we're seeing the same thing. And then it was like confession time, okay? And then slowly they realized that, this is actually really fascinating. This is actually great. This could be, if you're seeing the same thing, this could be really true. And then what does that imply? And the more we looked into that, the more we realized that, you know what? This solves all our problems. This is not a horrifying thing. This is a great thing. Now, there is a problem. We've got to account for it. Why? Why is the universe accelerating? It requires some kind of energy density in empty space. It turns out if you pack energy into empty space, perfectly empty space, that will have a negative gravity. It will cause space to expand all by itself. In this case, then, carrying its frame of reference and the mass that's in it with it. So this term was actually invented by Einstein long ago, the cosmological constant. We talked briefly about it when we got to our chapter on general relativity. That he thought for a moment it was his greatest blunder when Hubble showed the universe was expanding, and he didn't need this constant thrown in to just try and keep the universe from recollapsing on itself. And so he threw it away, but in fact, it turns out not to be his greatest blunder, but his greatest triumph. Could you imagine being so smart that even your greatest blunder is like 100 years ahead of your time? And I could only dream of that situation. Okay, so here's the thing now about this aspect of space. If space is expanding, then the energy contained in that space is also expanding. So it doesn't dilute away like matter, little nuggets of condensed things within that space. That would dilute away as there's more and more space between the matter nuggets. But no, this is space itself that has this property. And so the more it expands, the faster it expands. And the faster it expands, the more it expands. And it's a kind of a runaway process. An amplifying feedback, as we in climate science would say. So as the universe expands and gravity's grip weakens in increasing distances, it becomes more and more to be dominated by the unchanging expansion force of space itself. Okay, so is that the way of it? Is that really the way the universe is? Well, it needed a name, so we call it dark energy. We don't know exactly why it's doing this, but we have some ideas. So there's not only dark matter, but now there's dark energy too. But that just increases the mystery, so it just makes it all that much more fun to be an astronomer. So this is kind of a drawing trying to show the way the universe would expand, and we thought it would be expanding but slowing while it was expanding. That's the old classical standard Big Bang, but now we see that the universe is not the old standard Big Bang, but it's got this cosmological constant, and therefore the universe is accelerating as it expands. Now here's what that buys for you as far as our first cosmological problem. There's H today, okay? So there we are now. So the slope of that line locally is fit very well. We know what that is, and so all these curves fit to it. But now if you put in a differing amount of this dark energy, you see that it changes how old the universe is. The universe traces back to a different time, and it's farther back than you would have gotten with no dark energy. See? There's the 9 billion years that we were stuck with and we were agonizing about, because the globular clusters have got to be, younger than the universe as a whole, and they're like 12 or 13 billion years. Well, when we throw in the dark energy with a W of minus 1.0, which is what we got, what the observations say, and that's just exactly what we want. It takes us right back perfectly to 13.72 billion years. Nicely fitting with the globular cluster ages. So it resolves the age discrepancy, and now everybody's happy. The globular cluster age people are happy, the cosmologists are happy, everybody's happy. Except maybe Luke, I don't know. So, yeah, it doesn't thin out as space expands. It stays the same density. So it comes more and more to dominate the universe. So 11.5 billion years ago, dark energy was just a little teeny sliver of the pie, and most of the matter energy content of the universe was in dark matter. But as time goes on, it comes to be a thicker and thicker slice, and now today it's about 70% of the matter plus energy density of the universe. Now, I should tell you this. There's kind of two opposing aspects to this dark energy, whatever it is. It is energy. It is a positive energy. And as a positive energy, it has a gravitational effect. But because it's an energy in empty space, it has this negative gravity effect that actually wins that battle. But the point is that you really can add all of these together to get the energy density, matter plus energy density of the universe. And it turns out to add up perfectly. Okay, when Joel does with his Bolshoi, which just means big, Bolshoi simulations of a dark matter dominated universe, what you need to get the structure to look just like what we see in the real world, you can't, 95%, no. You only need like 25%. See? So maybe I'll tie in again why this dark energy solves the issue of clustering. So we thought we needed to solve clustering by having part of the dark matter be something that just refuses to cluster, namely the neutrinos. But instead, it turns out that the dark energy, which is forcing this new reacceleration of expansion, does the same job, and it does it without neutrinos. And in fact, so measurements today of the mass of the neutrino are not 5 electron volts. They're more like 1/100th of an electron volt, somewhere in that neighborhood. Okay, and if we go forwards in time, dark energy is going to come to be everything. So again, there's Darth Vader. It is our destiny. Now here's two opposing types of evidence that really nicely orthogonally intersect and give us a really clean estimate of the cosmic density of matter. And what do we get? We get about, sorry I can't draw a straight line, we get about 27%, I think is the favored number now. Drifts around a little bit as we get new satellite missions looking at the cosmic background. But that's about it. Okay? So galaxy clustering, this was the thing I used to be good at. Okay? That is telling us this. And the cosmic background radiation, which has lumps in it. But then the speed of the expansion, the other half of the situation, we got clustering, gravity, and we got the anti-clustering, the expansion. So that's told by the type 1a supernovae, and that gives you an arc like that. And so where do these both agree with the actual data? They agree in here. It nicely constrains where we've got to be, right about there. So we know we got 4% Here, there's 4%. There's the ordinary matter, this part of it. The dark matter is all here. There's the ordinary matter, only coming out to here. There's the dark matter, and then all the rest of this, all the way up to 1, which is off the frame, is all dark energy. So yeah, it's a little embarrassing. We don't know what the dark matter is, and we don't know what the dark energy is. So 96% of the universe is made of stuff that we don't really exactly know yet. But it does fit observations perfectly. It gives us a zero energy universe, and we know how to create a universe like that. But it's actually all good. So what is there any direct evidence for an energy density possessed by space itself? And the Casimir effect is related to that. So the Casimir effect is was predicted by this Dutch physicist way back in 1948. According to quantum theory, vacuum contains virtual particles which are in a continuous state of fluctuation. And if you get two things very, very close together so that you begin to exclude whole de Broglie wavelengths between those two places, then you begin to exclude a certain amount of this vacuum energy. And therefore you'll create an additional pressure on the other side of it, and it'll cause kind of an artificial pressure difference that is the so-called Casimir effect. And we see that. It's a quantum thing. I don't want to get too lost in quantum mechanics here, so I'm going to march on. Nice little electron micrograph of how you do that, how you measure it. These are little deflectable, bits of metal. And there's a little BB. It's not, I mean, it's way smaller than a BB, but it's kind of like that. And it's under a pit here. And by, the space available here is different than the space that's available out here. And so it excludes some wavelengths. And therefore there'll be less energy down here. And therefore this thing's going to feel a net force downwards that it wouldn't have felt without this quantum Casimir effect. An energy density in the empty space itself. Okay, what about standard Big Bang problem number 2? The horizon problem. Opposite sides of the sky are out of causal contact. And they have always been out of causal contact, meaning they have always been so far apart that no cause and effect from one could have communicated itself to the other of the two places that you're looking at. And because of the expansion, actually you don't have to be on opposite sides of the sky. You only have to be a few degrees apart, and you'll be out of causal contact because of the way that light will move through an expanding universe. So how could the universe be the same exact temperature to within 1 part in 100,000 on these places that have never ever been in causal contact? Now I know what you're all thinking. You're saying, well, Rick, wait a minute. Of course they were in causal contact. They all sat there at the Big Bang at the same moment. And they all agreed to be at the same physics, and then they all decided that they would just fly apart. Well, it's a very convenient little cartoon, but it's wrong. You can't do that. You can't do that. You have to remain in the universe while this is happening. So what you have to do is let the universe collapse onto you as you go back and back and back and back in time. And you can go all the way back to 10 to the minus 30th seconds. And still, these two places that you now see as spread far apart on the sky are still, even at their submicroscopic distance apart, at that kind of time, they still have not had enough time to come to the same temperature. Okay? 0 is not a time interval over which heat can travel and give you the same temperature from one place to another. I'm sorry. So, no, the horizon problem is a real problem. So then we get into inflation. And I always get nervous trying to talk about inflation because it just sounds like total crazy talk. Like I'm waiting for a student to pick up his iPhone and say, get the people with the white coats down here where our professor has totally lost it and he's, he needs help. It just sounds so crazy, and I always feel a little bit embarrassed. But anyway, I won't let that stop me. Now, we don't really know what caused inflation. But the idea of inflation is this. If you go back to a time even earlier than about 10 to the minus 30th seconds, that's decimal point with 30 zeros after it, and then a 1. You go back to a time before that, the idea is that the universe was actually in a state of so-called inflation. And it was expanding apart hugely. I mean, like 10 to the 60th, 10 to the 90th. I mean, the numbers are huge. Times faster than we're seeing now. And then it exited that epoch and it resumed the expansion that we see today, which is a normal Hubble expansion with a little bit of cosmological constant thrown on top. Okay, why did it do that? Well, one idea is maybe symmetry breaking into the force. May the force be with you. It is May the 4th. May the 4th be with you. Perfect time to be giving this lecture, I guess. Yeah, so anyway, symmetry breaking between what we postulate, it is only a postulate, that there may have been one force, grand unified force, and that the strong, weak, and electromagnetic forces were all unified into a single force. And when we got to a place that was cool enough, then the universe split. The forces themselves changed character, and you had now 3 forces instead of just, well, you had 2 forces instead of just 1. The so-called grand unified force and then gravity. Start with 2, and then you get 3. The strong electromagnetic, well, the electro-weak force. Later, you get to a point where you actually split off the weak force and the electromagnetic force. I didn't tell you that yet, but anyway. So symmetry breaking between the symmetry of the forces might have been an instigator to this, or just some kind of a quantum fluctuation. So before I talk more about why inflation might have happened and what it really means, because it's kind of spooky, I think what I'd rather do is just give you really solid evidence that it really did occur, so that it doesn't sound quite as crazy, because otherwise it just sounds like, you know, reaching for the wild blue yonder to explain problems that you can't figure out any other way, like the horizon problem. But if inflation really happened, it predicts that the density of the universe is precisely at the critical density. That's one prediction of inflation. So if we could measure that the density really is at the critical density, then there's actual independent observation. Okay, Josiah, you have a question? So the universe was inflating, stopped, and then starting? Yeah, it didn't really stop. It kept expanding, but only at this much slower rate. It exited the inflationary epoch into the kind of the current universe that we have today. Still expanding, but expanding at a much more leisurely pace. So why would it do that? Again, we're going to talk about that later. Okay, so there was another problem I didn't mention yet. I probably should redo this whole thing. I need to get all the problems out first. But the other problem is, where do galaxies come from? So you're picturing this universe, and you saw that graph of temperatures, and you're imagining a gas that's at temperatures of, like, 10 to the huge exponent degrees. How could you possibly have lumps in something like that? Matter is so hot that stuff is zinging around so fast that you wouldn't. How could you have lumps? How could the universe ever have turned into galaxies? Why isn't the universe just dark matter flying apart at large speeds and individual ordinary matter flying also? Where do you get the lumps? We're going to look at the cosmic background radiation, and the cosmic background radiation is already lumpy. It's already lumpy. And it's lumpy at a low level, but a level that we can only account for if the dark matter itself is already lumpy. And where did that lumpiness come from? Well, we have an easy explanation, actually. During the inflationary epoch, the universe was so tiny that its physics was really dominated by quantum mechanics, the quantum uncertainty principle. So while we're saying, okay, yeah, density was the same everywhere, but it's only the same plus or minus this quantum uncertainty. And that means that in a very real sense, the density is kind of undefined, or it is randomly moving from one value to another within the quantum uncertainty tolerances. Now you take that and you expand it really fast so that the size scale is not subatomic in the quantum realm, but is now big. Now you're no longer in the realm of quantum mechanics. Quantum mechanics kind of rules things at tiny scales. And so it's like this Deuce's Wild random white noise density fluctuation back and forth faster than you can say the words, all of a sudden gets frozen. It gets frozen in and it stops fluctuating because it's now so big that it can't fluctuate. And now those lumps in the quantum realm have turned into galaxy-sized fluctuations in the density. The density, in this case, of the dark matter. And those density fluctuations in the dark matter then acted as the gravitational magnets to allow the ordinary matter, once it finally cooled enough, and of course that took another million years or so to get to that point, that it could finally begin to fall into the pre-existing lumps. See, the dark matter doesn't care about the temperature. Okay? Doesn't feel the strong electromagnetic force. Temperature is not really its bag, okay? And so those dark matter lumps were already there, and they acted as the seeds into which the ordinary matter could fall in. Instead of the ordinary matter having to look around and say, okay, where's there a lump that I can fall into, and seeing everybody else zooming around so quick that there weren't any lumps. And that really slows down the rate at which you can make lumps. And yet we see galaxies forming very early in the universe. And we see the cosmic background radiation already lumpy. And so the question becomes, where did those lumps come from? There shouldn't be any lumps. But there's lumps. And they came from quantum mechanics. Okay, here's an old slide, and I just want to show you, it's kind of early evidence that, look at this. The cosmic density parameter, another way to say closure density, is omega equals 1. And this particular, I don't think this is a super great distance indicator, but anyway, there's already evidence that, yeah, that falls nicely along a closure density universe. And I forget the date of this thing, but you can already tell it's old. It's probably at least 25, 30 years old. It's 7:30. I actually want to keep going. You don't really have to, well, actually you do have to see your video now. Because I don't want to keep you, I can't keep you after 9 o'clock, that's illegal and immoral. Okay, so I am going to pause this. This will be Cosmology lecture number 2. It looks like this Cosmology lecture is going to be in 3 parts, not 2. Okay, so I am going to stop the meeting. I'm going to do that right now.